All right, guys, so this is chapter 15, part 4. Disturbing a reaction equilibrium. So this is Le Chatelier's principle, okay? And it basically says when a chemical system is at equilibrium and it gets disturbed, the system shifts in a direction that minimizes the disturbance. And so the reaction has to get back to equilibrium. It's going to do whatever it has to do that. So let's look at this closer. All right. When we change the concentration of something or we add something to the reaction mixture, it's going to go away from an increase. So if we add more NO2 to this reaction and it was already at equilibrium, so it's already been allowed to sit until it's reached equilibrium, the reaction is going to shift left. So if it shifts left, that means that the NO2 in the system will go down. This will decrease in concentration. And this will start to increase in concentration. And it's going to do that until it gets back to whatever K was. Until it gets back to equilibrium. So if this was already at equilibrium, and then we add more NO2 to it, so more of that NO2 is put in there, then it's going to start creating more product and shift this way. So it's always going to go away from an increase. Just like down here on the bottom, same reaction, but if we add N2O4, the reaction will shift forward. So if this goes up, it's going to shift away from an increase so that this goes down and the product goes up until it reaches equilibrium again. All right, now another way we can affect equilibrium is to change the volume of a gas. So a decrease in volume causes an increase in pressure. And an increase in volume causes a decrease in pressure. Remember, pressure and volume have an inverse relationship. It's Boyle's law. I know we didn't learn all the different laws, but we did learn about the relationships between them. And so if one goes up, the other has to go down. And so from the ideal gas law, we can see that lowering the number of moles of a gas results in a lower pressure at constant temperature and volume. So a system can respond to a disturbance by changing the moles of a gas present to relieve pressure change. All right, and that sounds all very complicated, and it's really, really not. So if we have this reaction happening, and they've decreased the volume, so they've allowed the reaction to exist in a smaller amount of space. Well, which side of this reaction do you think takes up a smaller amount of space? This side of the reaction, the reactant side, has 4 moles of gas total. It has 1 N2 and 3 H2, whereas the product side of this reaction only has 2 moles of gas present. So if we give it less space to move around in, it's going to go to the side with less moles of gas because it has less space to exist. So it's going to shift forward. On the other hand, if we give it more space to exist, then it's going to take up that space and respond by shifting to the side with more moles of gas. So if it has more space, it goes to the side with more moles of gas. If it has less space, it goes to the side with less moles of gas. And that's really it. That's all you have to know. If it had equal amounts of gas on both sides, there would be no change. It wouldn't affect the equilibrium at all. Now, temperature change is another way we can affect equilibrium. And the reason that this affects equilibrium is because it changes K. It doesn't just change the reaction position. It changes K. So an exothermic reaction, heat is a product. It's on the product side. So if you look down here, right here, heat is a product of that reaction. And so if we increase the temperature, we're adding heat to the product side, and it's going to shift away from an increase, and it'll shift to the left. It'll shift to the reactant side of the reaction. If we remove heat from that side, so we're still talking about an exothermic reaction, if we remove heat, it's going to shift to the right to replace the heat that's been removed. In an endothermic reaction, we can think of heat as a reactant. So in an endothermic reaction, heat is on the reactant side, and so if we increase the temperature, the reaction is going to shift to the right. And if we decrease the temperature, it's going to shift to the left to replace the heat. So it's going to make more heat. So if we make the reaction colder, we're removing heat. And so it'll shift towards whatever side heat is on. So to summarize, if we add a product, the reaction will shift to the reactant side. If we add a reactant, the reaction will shift to the product side. If we remove product, the reaction will shift to the product side to replace it. If we remove reactant, the reaction will shift to the reactant side to replace it. And decreasing the volume causes the reaction to shift in the direction that has fewer molecules of gas. Increasing the volume causes the reaction to shift in the direction that has more moles of gas. If a chemical reaction has an equal number of moles of gas on both sides, a change in volume has no effect. And then exothermic reactions, increasing the temperature causes the reaction to shift to the left. Decreasing the temperature causes reaction to shift to the right. And endothermic, it is the opposite of that. All right, so we're going to look at these examples, and it says, what is the effect of adding more CO2 to the reaction mixture? So if we add more CO2, this will go up, the reaction shifts away from an increase. So it will shift to the left. So it'll shift to the reactants or shift left. What is the effect of adding more CaCO3 to the reaction mixture? So in this situation, we're going to be adding CaCO3. That will have no effect. And the reason it doesn't have any effect is because it's a solid, and solids they don't affect equilibrium because they're not in the K. So that's the only thing you have to watch out for that wasn't really discussed in the context of the video so far. But I'm telling you right now, if you add solid to an equilibrium mixture, it's not going to affect it. Now, if we remove CO2, so in the next one, if we remove CO2, it has to replace it, so the reaction would shift forward. So shift toward product, or forward, or shift right to the right. Consider the following reaction at equilibrium. What is the effect of decreasing the volume of the reaction mixture? So we're giving it less space. And so if it has less space, then it's going to move to the side with less moles of gas. So I have 0 moles of gas on this side, and I have 3 moles of gas on this side. So if it has less space, it's going to shift to the left. And what is the effect of increasing the volume of the reaction mixture? So now it has more space, so this will shift to the right because it has 3 moles of gas on that side and no moles of gas, 0 moles of gas on the reactant side. Which change would cause the reaction to shift to the right? So we're looking for what's going to cause the reaction to shift to the right. So if we decrease the volume, I've got 2 moles of gas here, and I've got 2 moles of gas here. So that means that changing the volume is not going to shift it in any direction because there's 2 moles of gas on both sides. So this won't cause it to shift towards the product. This won't cause it to shift towards the product. And then C says increasing the concentration of hydrogen gas. If we increase hydrogen gas, H2, the reaction will shift forward. And that is shifting towards the right. So that will do it. Decreasing the concentration of hydrogen gas would only shift it towards the decrease. And so that's not going to affect it. All right, so in this reaction, CaCO3 is endothermic, which means if it's endothermic, heat is going into the reaction. It is a reactant. And it says, what is the effect of increasing the temperature of the reaction mixture? So if I increase the temperature, the reaction is going to shift forward. So it shifts to the right. And decreasing the temperature, so if I decrease the temperature, the reaction would shift to the left. What would be the effect of increasing the temperature of the following reaction? So here I have an exothermic reaction, because it's exiting the reaction. It's a product of the reaction. So if I increase the temperature, then the reaction is going to shift to the left. And that means I'm going to make more SO2 and O2 and consume SO3. So it'll eat up that heat